All right. Thank you for coming to the Talent Pavilion booth. In this session, we'll be talking about the quantum cybersecurity as a career led by Dr. Tan Teck Guan, the CEO of PQC. The silence conference will now start.
So I'm testing my mic right now. I hope you guys can hear me clearly. That's nice, thank you. And if you guys have any problems with the audio, do just raise your hand so that we can try to fix it. But thank you for coming, and it's great to see so many young people really trying to come into this thing because it's an area that's going to happen in the next 5 to 10 years, and it's great that you guys get prepared for it. So my name is Teck Guan. I'm the CEO and co-founder of PQC. And my email is here, so if you have any queries or any kinds of questions that may pop up after this session, I'll be happy to take them. You can also connect me on LinkedIn. Just mention that you attended this, and we can also chat over that. So let me start by having a clicker to convert. To move this. So my program today will be on 4 parts. I'll give a small introduction about quantum computers. Let's be clear, we're not going to be able to cover everything about quantum computers. You're not going to have a PhD in quantum computing after this session, but it's just a little flavor of what you have. The highlight of this is I want to be able to do a hands-on with you. For you to be able to run a very simple quantum program where you are sitting right now. And that's something that I want to do. And I want to try this out. This is the first time we're doing it. Hopefully that gets to work. So if you have your handphones with you, that will be something we'll do. I will also cover the threats and some of the considerations throughout the quantum journey that we'll talk about. So let's start with a quantum computer. What is a quantum computer? I mean, everyone asks the same question. So let's start with this. A few things, a few words that you probably want to understand. It's the difference between a bit and a qubit. So quantum computers store data in qubits. It's short for a word, quantum bits. It's a bit different from your current laptops, your handphones, your cloud, where everything is stored in just bits of zeros and ones. In a qubit, it is almost a 3-dimensional thing, right? So imagine a bit as just a line between 0 and 1, where there are only 2 points to it. A qubit is essentially a sphere, a ball. And the value can be anywhere on the surface of that sphere, so that it's a much larger amount of data that can be stored on a single qubit. If you're trying to map between a digital bit and a qubit, it is an exponential thing. 1 qubit can be represented in 2 digital bits. 3 qubits, 8 digital bits, maybe not so big. But once you start to go like 20 qubits, you realize that when you go 20 qubits, it's already 1 megabyte. 1 megabit already. And so as that exponential thing goes up, imagine now something having 1,000 qubits or 2,000 qubits. Something that has 2,000 qubits is more molecules than anything in the whole Earth right now. That's the kind of exponential growth we can see with just the data storage point of view. If you couple now the data storage with the compute capability of a quantum computer, that's where gates come in. So maybe in high school you learn about physics where you have your gates, your AND gates, OR gates, NOT gates. In quantum computers, we are also using gates. But these gates are a bit more special. They have like Hadamard gates, control NOT gates, and a few others that will help you perform 2 things. Put the qubit in a state of superposition. That means to move it not just from 0 and 1, but to somewhere on the sphere itself, where that value is quite unpredictable right now. The second is the entanglement side, where they can connect 2 qubits together, such that when you manipulate one of the qubits, the other qubits also changed at the same time. And this is where the speed up happens. Right, so just combination of qubits with superposition and entanglement, these are really the 3 principles you need to understand when you go into a quantum computing side of things. And what really comes out of it? Really the speed up. 1, more data. I mentioned already, quantum computers with qubits store a lot more data compared to a normal computer. 2, faster processing. When the qubits are entangled and you just change 1 qubit, the rest of the entangled qubits also change correspondingly. All right, so it's a bit different now. If you use your current computer right now, you change one thing, you open your Word document, you change 1 word there, all your other documents don't change. It's still only 1 document. But if they are all entangled, changing just 1 qubit manipulating it in a way mathematically, makes all the other qubits that are entangled also get manipulated at the same time. And this speed up allows us to then manipulate and create a much faster and much more powerful way of doing computation. So these are two things, right? More data, more processing. And with more data, more processing, wow, we start to do a lot of things. Today, we are already talking about CPUs and GPUs, right? I mean, if you guys had bought NVIDIA a couple of years ago, you guys are very rich. You don't need to start, don't need to work right now. But the next thing that you're going to see, a QPU, a quantum processing unit. So we expect then CPUs working with GPUs, working with QPUs now to do even more processing, to do solving problems that currently cannot even be imagined to be solved right now. And that's really what we hope to see as the future of quantum. And the world is not stopping, right? So every year, hundreds of billions of dollars are put into research by both governments and the private enterprise to do quantum research. And these hundreds of billions of dollars is not just going to waste, right? I mean, they're going to translate into new types of applications. If you follow what McKinsey is estimating, they're thinking that by 2040 to 2045, they're looking at potentially $9 trillion worth of new applications that are coming out because of this itself. So this is a crazy number that people are expecting maybe in the next 20 years. But if you don't start today, we don't want to wait until the quantum computer is there and everyone's figuring out what to do before we start to do something. And that's where we want to come in and we want to start doing this. If you are looking at some of the vendors that are working on quantum computing, Google, right? IBM, Google, Microsoft, AWS, Quantinuum, these are already the usual suspects. They've already pumped in billions themselves in order to get this done, and they're continuing to do so. To get access to these, unfortunately, are a bit more difficult, right? I mean, they are ultimately still very expensive machines. So what do we turn to? We turn to simulators. Simulators are essentially quantum computers, but running in software, to perform the same thing as per hardware, but in a very simple simulator environment in order for you to appreciate and understand it. And it's an easy way for many people to start the quantum journey itself. And so today, I'm here to show you what we have. QuickScript is a simple quantum simulator. We simulate 20 qubits on your phone that can be used to start to write programs, and you can start to discover it. So let's start, let's not waste time. Let's start with our very, very first quantum program. I will introduce you to this gate called a Hadamard gate. A Hadamard gate puts a qubit, say from state 0, into a superposition that can have a 50% chance of getting 0 or 1. If you scan this URL right now, you will load a page. You will load a page that will give you something like this. This is the simulator kind of thing that you have. And this yellow box, the yellow box in your web page, is actually a 20 qubit quantum simulator. You literally can run it there. And if you go click the run button, you just go click the run button, you have actually run your very first quantum program. Welcome to the group, right? You are no longer a quantum newbie. You are now a quantum programmer because you've just run your first program. What does this program do? It doesn't do much. You have 3 qubits, and in these 3 qubits, you have an equal chance of coming out with any kind of number, from 000 to 111. So because Hadamard gates is a gate that puts a qubit into a pure superposition, it allows for you to be able to get to a random state that you can use. So if you want to use a quantum computer as a random number generator, it's a very expensive random number generator, you have figured it out. It's just using Hadamard gates. That's it. Simple. But that's not where we want, right? What I want you guys to do is to do the next program. The next program is much more interesting. This is called the Hello World. So the Hello World of quantum computing, right? So in all kinds of languages, they want you to learn your very, very first useful program. In C, you write a program that prints out the word Hello World. In quantum computing, what we want to do is to create a Bell state. Okay, so a Bell state is essentially to put 2 qubits or more into a fully entangled state, where the possible results when you run the program is either 00 or 11 because they're entangled. It cannot be any other result. Huh? Just now when you use a Hadamard gate, you you can use, it can be 0, 1, it can be 1, 0, it can be all the other permutations. But in a Bell state, 0, 0, 1, and 1, 0 are not possible outcomes at all because these two qubits have already been entangled using this very special gate called the control NOT gate. Okay, so if you are already scanning there and you are already getting this thing, I mean, who's managed to load the program and actually run it? Welcome, welcome. Wow, I mean, maybe the next time I will do a Guinness World Record, right? The number of the most number of people doing running a quantum program at the same time. I think we will be part of the books itself. But this is really where we think you can start to understand a bit about quantum programming, a bit about what quantum computers can do that normal digital computers cannot do. Because a Hadamard gate or a control NOT gate don't exist in a normal digital world. And once you start to understand the power of this and you start to understand more and more of the more complex gates, which gives you the rotation across the different axes, then we start to write really, really complex programs. But I do want to just give a little pause here to make sure that people, I didn't fly through this thing. Anyone facing problems loading this thing? Anyone facing problems trying to see, do I need to repeat this again? Everyone's happy? Good. So all of you have managed to run a quantum program already. All of you have managed to get the hello world out. You can now post it on Facebook or post it on Instagram and say, yay, I have run my very first quantum program. And that's really what we want to do. We want to bring across that it is actually not so scary. Okay, eventually quantum programs will get much more complex and stuff, but you always want to start from the basics. And really my message today is it's not so difficult after all. Understanding quantum programming, understanding quantum computing is part of this journey that we want to do into the quantum cybersecurity. And so therefore you probably ask like, so what's the implication? Just because I can run a quantum program, what does it mean from a cybersecurity standpoint? This is where it starts to get complex. So if you are going to leave this workshop and you want to remember just one word that people say, what did you learn today? Shaw's algorithm, okay? Professor Peter Shaw in 1994 came up with a quantum algorithm, and you see that it's a bit more complex than your hello world. It's more complex than your Bell circuit. He came up with an algorithm that can be used to break public key cryptography. This circuit that you see here is used to factorize the number 21. And using this circuit, if you follow this circuit and you run it on your phone, you can actually come out with the results of 3 and 7. I know that we learned in primary school that 3 times 7 equals 21. But quantum programs can also do that. And they do it in a way that's faster than a normal digital computer. Exponentially faster. And if this is then extended to become bigger and bigger, that once we have a quantum program that can run thousands of qubits, this same program can now be used to factorize a lot of the public key cryptography applications that are being used today. For example, web browsing. You know, you open your web browser and you see that little lock at the top of the corner beside that URL that you type. That lock relies on public key cryptography in order to ensure that it is secure. But with a quantum computer, that lock is no longer useful. Unfortunately, it can be broken. Similarly, for other kinds of applications, from your document signing, from your identities when you're trying to log on to your internet banking, to your government identities, a lot of all these different data security implications will be impacted, unfortunately, because of Professor Peter Shaw. I mean, he's a good guy, right? I mean, he came out with this that we understand what can be done. And so therefore, understanding what is the threat today and understanding what we can do about it is really part of this whole journey of being a quantum cybersecurity professional. Okay, so this is one of them. There is another algorithm as well, Professor Lou Grover, who came up with an algorithm to do brute force searching. So if you want to say, hey, I want to go into quantum, but I'm not so much into the cybersecurity side, I want to do a bit more AI, machine learning stuff, you probably will start to learn about Grover's algorithm as well. And again, The link is there. We have some sample code, that sample scripts that you can do. Go try it out, go run it, and you start to understand a bit more. And it's not so scary after all. Okay, so these are the two really, really very popular or famous quantum algorithms that make the difference between someone who understands quantum and someone who is totally a newbie to it. And I've tried to make it to be as simple as possible to you so that you can go back and say, hey, I know how to break I know how to break public key cryptography already. Shaw's algorithm, right? That's all you need to know. And everyone will think that you are the best thing since sliced bread, right? Okay, but I'm joking. What exactly does breaking public key cryptography actually mean? That's probably a question someone will ask you immediately, right? So I'll teach you the answer as well. Okay, so let's go into the thread itself. I said before, public key cryptography can be broken with a quantum computer. Whoa, what does that mean? Okay, we use a lot of all these keys and how will they flow here and there, and sometimes it's not taught in school, sometimes it's taught in schools. Wow, it's so confusing here and there. Let's go a bit into the practical side. Let's go into the flow side of it. Okay, so how about your data? How about your data encryption? So there's the two, Alice and Bob. And Alice is trying to send some information, some secret information to Bob and say, hey, I don't want anybody else to know. I just want two of us to know this thing. So there's a confidentiality problem. And they use public key cryptography. So there's a message to be sent. What happens is that Bob shares his public key to Alice. And Alice then uses the public key to generate a session key and then encrypts the session key using the public key and sends it over. This is already done, for example, in your internet banking. If you go and try your internet banking now, and you enter your user ID and password, if you're still using passwords, on your web browser itself, the web browser uses the bank's public key to encrypt this PIN and then send it over to you. Okay, so that's how it's protected. And this is good. This runs normally every day for the last 25 years, and for the next 5 years, this works. Unfortunately, with a quantum computer, what happens? Eve has a quantum computer, and Eve is currently harvesting the data. Eve is collecting encrypted data. So it's encrypted. She cannot see it now. She's collecting the data today and storing it. Perhaps you are doing your internet banking on Starbucks or in a hotel Wi-Fi or in an airport Wi-Fi. This data can be easily collected. Eve cannot do anything about it yet. But when a quantum computer is powerful enough, maybe in 5 years' time, Eve is going to take the public key and calculate the private key from using a quantum computer. This is when bad things happen. Because now Eve has the private key, and Eve has the collected data that she collected 5 years ago. And then, and now she starts to be able to see everything from your pins to any kind of data that you're going to transmit off your website. All of these, unfortunately, can be seen. So whatever you're doing today, if you're using a public Wi-Fi, please be mindful that that data can be harvested today and decrypted in, say, 5 years' time. Maybe don't do certain sensitive stuff over public Wi-Fi. Even though you see the log, try not to. Okay, that's one thing. From digital signing or identities, there's also another threat, right? You use DocuSign, or you use some PDF documents, or you're using some, basically a way to identify yourself between two machines itself. On the other, now Alice is sending the same message to Bob, but Alice wants to prove to Bob that it was from her. Bob wants to know that this message came from Alice. It didn't come from anyone else. It's not some malicious person that's doing it. So Mallory is going to try to pretend to be Alice. What Mallory will try to do is from Alice's public key, calculate Alice's private key using a quantum computer. So this happens perhaps in 5 years' time. And now Mallory can send anything to Bob pretending to be Alice. And this is really a scary part, right? So now Bob receives a message saying it's from Alice and doesn't know, is it from Alice or not from Alice? I'm not sure. And this is scary, right? So Mallory can do one thing, and this is one threat. The second threat that we're seeing is that now Alice can pretend that it's not from her. She sends something to Bob, And then in 5 years' time, denied that that was sent by her. She said, no, it was Mallory who did it, not me. Right, that non-repudiation part of the whole cybersecurity, of cryptography, is broken because of quantum computer as well. And that's something that we don't want, right? I mean, businesses rely on trust. I trust that I know the person I'm talking to. I trust that the message that was being exchanged by two of us was never modified. I trust that that message was never revealed to anyone else. And a lot of this trust that we talk about from a digital standpoint is no longer going to be secure because of quantum. So is this a good thing or a bad thing? Well, I mean, my startup, we work on post-quantum solutions, so I see this as an opportunity, right? I mean, this really opens up an area for a new generation of cybersecurity and data security professionals to come in and solve these kinds of problems. Okay, so that's really it. In the next 5 years, this kind of demand is going to be crazy. I was predicting that in 5 years' time, you will start to see job ads that says, I need to hire someone with 5 years experience in quantum cryptography. Oh, that means you must start today. You can claim that you start today, and then in 5 years' time, you have 5 years of experience in working on it. Because that's something money cannot buy. You cannot turn back time in 5 years to say, let me get back that experience. It's currently not taught in schools. A lot of the cryptography is not taught in schools. A lot of things it's not taught anywhere. You literally have to be, doing your master's, your PhD, or maybe even working within your organization that may be working on these kind of projects. They are few and far between, but starting on this is a very important thing. So with all the risks and everything here and there are a lot of kinds of work that can be started in it. It can be from risk identification. It's not so much as solving it. Risk identification by itself is already a very important thing. Many of the banks, governments are starting on this, what they call a asset prioritization or asset inventorization, where they start to go into their existing systems, and this goes into their cloud, their applications, their emails, their data storage, their backup, their recovery, and going to see where are the areas that are vulnerable. Where are our risks? Can someone impersonate this? Can someone steal this? Am I going to be faced with a problem in 5 years' time that someone is going to do a ransomware on me because they stole some data that cannot be revealed? All these kind of work, really just at the preliminary level, is already driving everyone nuts because there's so much work that needs to be done. And it literally has to be done yesterday, I would say, but... And therefore, the opportunity comes in. Beyond the risk identification, then it's about fixing it. There are already new algorithms, like what we call PQC, or post-quantum cryptographic algorithms, that have been standardized. If you are a bit more in the computing side, the more mathematical side, start looking at these three algorithms. These have been standardized by the National Institute of Standards and Technology, the good guys in US. It was done over a 7-year period since 2016 till, so 8-year period, 2016 to, and just announced in August of this year. So these algorithms are so new that they have just been announced 3 months ago. Okay, they were not taught in schools. You go pick it up, you go learn. If you are a programmer, go to openquantumsafe.org. A reference implementation of the code is there. You literally can start using post-quantum cryptography from your laptop, from your cloud, and you can start using it. Get that experience, build in that capability, and that is going to serve you very much in the longer term. I provided these two links. This provides you sample code on how to get it done. If you want to follow the standardization and you are a bit more in the technical side, go to the Google Groups. Again, very open. Go study what they're doing. Think about what they are, read, listen, understand what they're doing, and you can even do more. Singapore-wise, we are working on the National Quantum Safe Network. So NQSN, the Singapore National Quantum Safe Network, is another way of solving it using quantum key distribution. And Singtel, SBTel has already started the process of building these networks in Singapore itself. If you want to understand about QKD as well, please go to this URL, start learning about it, because that's going to be big. IMDA has invested over $100 million just to set up this network, and they continue to put in more money into this thing itself. So it's not a trivial amount of money coming into this. And they do need engineers doing QKD. The Currently, the only engineers doing this have a PhD behind their back. But we're trying to say it's actually easier than that. You can literally start working on it, and that's what I'm trying to encourage you to do. But if you think that these are still too technical, there are actually a lot of other things that need to be done. If you look at the time frame of what we think will happen over a quantum kind of a period, it can be from, if we work backwards, say 2031 is when people think quantum computers will be available to do bad stuff. And this is the same working timeline by the US government and several of the other governments. If you work backwards till today, you're going to see that there's going to be a need for a lot of risk awareness. There's a lot of kind of understanding of where your current situation is and what are the types of things that need to be done. And my prediction, 2028, there will be a crazy shortage of quantum talent. Not today. Not today, but build up this expertise. If you have 3 years to build up till 2027 or 2028, my bet is that your CV will be a very, very valuable CV in 3 years' time. And that's really the message that we want to bring across. A lot of the resources can be available online. Go learn, go study, go try it out yourself, and that's going to be very useful. And it's not just, again, on technology. Imagine the legal requirements. Imagine the compliance. Imagine how this impacts your AI LLMs right now. Imagine a lot of the environment, a lot of the other budgets, crime that will come in, and all these kind of considerations. I have only used technology over the first few slides, and I think that's already very overwhelming. But there's so many other considerations that need to take place because quantum is going to impact this multi-trillion-dollar digital economy. Okay, and in so many ways beyond just technology, and this is where we really want to encourage more people to take that first step. Learn, go try, go do. And finally, as a plug here, so there are some links that you can try. You can go and do this. There are already, if you have your skills future, these are courses that you can literally also go on, go try it, go spend some money. Or if you don't want, there's lots of resources online that you can do it. So I think I still have about 10 minutes for Q&A, and I wanted to do Q&A, but yes. Hold on, I have a gentleman who is supposed to run with a mic to you, so because it's all silent, I can. Okay, you can scream.
Yeah. What do you think about quantum biometric identification?
Quantum biometric identification. So the question is, what do I think about quantum biometric identification? Thank you for your question.
Yeah, can it be combined? I mean, quantum biometric identification, which is biometric identification, is also on hype now, so it is spreading a lot.
Okay, so I will be frank with you. The good guys at NIST, the National Institute of Standards and Technologies, the good guys at IETF, the good guys at ISO have not even started considering biometrics with quantum. It is still something that is in their roadmap. There's so many things to do. If you just try to go and see what IETF is doing, they have close to 20 different work streams just to figure out the cryptographic algorithms, not yet biometric, just public key cryptography. They have 20 work streams to try to figure out how to get these public key algorithms into your SSL, into your secure emails, into all your internet protocols and crazy. Biometric passwords, what's the impact of biometric and passwords from a quantum standpoint? Potentially, your passwords may go from 8 characters to 16 characters because of Grover's algorithm. Biometrics probably will have to go down that same way. There are currently no standards in that area. If you have an interest in it, I would say go ahead and go study on it. It's definitely something that no one has really even touched at any level. There are some research papers, and everyone's trying to vie for their own standard to become that number one. Lots of opportunities there, not yet available. Yeah. Any other questions? Yeah.
Hi, may I ask, for us, the four of us here, we are sitting as like 15-year-olds and still in secondary school. So we're wondering that since by 2027 we have graduated JC, so what can we start at our age right now to prepare ourselves to be quantum ready, other than those links that you have provided above?
Okay, thank you very much. Wow, I'm so glad that you guys want to start early. Within my start, personal experience. Within my startup, we actually take in 16-year-old interns to come in and teach. So they come in for about 2.5, 3 weeks. What we put them through is to learn about quantum and create courses to teach their fellow students and teach their teachers about quantum. Because it is so new. Your teachers have not even learned about it. They don't even know about it. You go ask your teacher now, teach, what is quantum? They will look at you like, So we have actually brought in interns and they created courses. They create a simple 1-2 page course to teach their students, to teach their fellow friends, and to teach their teachers about quantum. And it's the understanding that embracing quantum, that it is not a scary thing. It is not something that that only need PhD to do. That a 15-year-old, 16-year-old high school student can literally understand the concepts. It's something that we will definitely help to contribute in Singapore and really make Singapore a next level of where we are right now. So I would say go ahead, go learn something. And if you have some content that you want to put up to teach the rest of the world, I'll be happy to host your content for you. Yeah.
Thank you. Yeah. I'm a big fan of quantum algorithms, and my question is, how many qubits the most powerful quantum computer has now, and how many of them do we need to break like 99% of classical security algorithms, and how much time do we have to secure ourselves from quantum hackers?
Okay, 3 questions. The first question is, how many qubits are there today, right now? So there are different quantum technologies being built by the IBM, by Google, by AWS. They are all pursuing different tracks in how they do it. So IBM is pursuing something called superconducting qubits. And that by far is able to scale the qubits much more than this. They are already announcing 1,000 qubit, physical qubits for superconducting. But what we are looking for is called a logical qubit. A logical qubit means something that's not noisy, right? Current physical qubits are noisy. That means that you put a value inside there, within a few milliseconds, boom, the value is gone and is useless at all. They need it to be logical, and therefore they need a lot more qubits just to make one logical qubit. There are other technologies like Continuum that's using trapped ions. They are also using Pascal that's using neutral atoms, and quite a few others as well. The current state of the art is we are looking at somewhere between 50 to 100 logical qubits today. So there are already 50 to 100 logical qubit quantum computers that can be used for computation. To put in perspective, a large supercomputer in Singapore, the largest supercomputer in Singapore, put together, can only barely do 40, 45 qubits. So the current quantum computers out there are really more powerful than the supercomputers that we have right now. Second question, how many qubits does it take to break the cryptography? So it depends on whether you're doing elliptic curve or RSA, but for 256-bit, so the smallest, let's look for smallest. The rule of thumb for elliptic curve is 6n plus 2. So 6 times 256 is about 1,600 qubits. So once you hit about 1,600 to 2,000 logical qubits, bad things will happen. So that's the current state of where we are right now. Okay, and sorry, what's your third question? How long do we have? Just Google online. Gartner says 2029. Google Gartner post-quantum, you'll see the date come out 2029. IBM's roadmap for a 2,000 qubit computer, 2033. So somewhere around then. I would say it's within our lifetimes, I would say. Okay? More questions, sorry. How are we doing for time?
Hi, sorry, I
Yeah.
have two questions. So the first question is, what are the job opportunities in this field apart from research work?
Yeah. Job opportunities. I sort of came up with something like this, right? I mean, imagine the kind. It's currently quite it's quite a green field right now. You literally can create your own. You know, just like when ChatGPT came out, prompt engineering became something that became a job that no one expected it to be. In quantum, will there be new jobs that will be created? I'm very sure there are. You know, my gut feel is that there will be new kinds of scams that first come out, just to tell people whether is it a real quantum or fake quantum. You know, all these kind of scams will start to come in. Do you need people to detect these kinds of scams, to teach people what to do? I'm very sure there is. There will be a very big area on simply marketing and awareness, explaining to many of the older generation like myself what is a quantum computer. I learned a bit more, so you don't have to explain to me. But many of my colleagues, many of my peers didn't grow up with that. Cannot understand anything beyond a digital computer. You know what we do learn in school? We learn what is an analog computer and what is a digital computer. Now what is a quantum? Oh my God. I cannot even imagine that. I cannot even imagine what it means. And just the awareness and marketing side is going to require a lot of people to change their mindset, to be able to understand what it means to be. And so therefore explaining it at high school level, explaining it for different industries. Imagine the kind of work that needs to be done. From a legal compliance standpoint, everyone needs to migrate, everyone needs to upgrade. Do we know we have upgraded correctly? Do we know we have migrated correctly? Compliance-wise, how about legal? Someone starts to dispute because I mentioned, right, you know, Alice sends a message and now she denies it is. Will there be new legal fields in how to draft these kinds of things? Look at PDPA, the protection of privacy. If I'm collecting encrypted data today, and this gets shown in 5 years' time, the organization who has that data, are they liable for PDPA? We do not know. We do not know. All these are stuff that's totally silent. We haven't even figured out how to even get through this right now. So your guess is as good as mine. You probably come out with a job that I don't know as well. I don't know. Maybe the next generation of Instagram that teaches about quantum and stuff. I don't know, but I would say it's a green field right now.
Thank you. I have one more question.
Yeah.
Is it possible, or is there any hope to link quantum to other industries like healthcare industry?
So yes, so we didn't cover the use of quantum, right? So quantum is currently used in three broad areas. In finance, where they're using quantum computers to detect fraud, to balance their portfolios for optimization. In healthcare, they're using it for drug discovery, right? So we're trying to find new drugs using quantum computing. They're using quantum sensing to detect for cancers, for example, using these kinds of things. So that's really deep research. You probably need to get your PhD to do that, but that's an area in healthcare. And finally, in manufacturing and process engineering, there's a lot of optimization that needs to be done. How do we speed up that process, which is very manual right now? How do we improve these kinds of combinatorial problems? And that's where a lot of problems come in. So if you look at QUBO problems, QUBO problems, these are again all things that they expect quantum computers to solve. So a lot of that area in the using of quantum computers for good. We are here. I was talking about the bad stuff that we want to fix, but yes, there's a lot of good stuff as well. You have a last question?
Oh yeah, hello. So you mentioned that quantum computing would weaken hashing. So what do you think about like the future of blockchain technology now that a lot of the current financial systems and banks are shifting to it?
Yeah. Well, so in blockchains itself, the weakest point in blockchain is the digital signature they use. Right? So blockchains use ECD as an elliptical digital signature algorithm, and that is not quantum safe. So blockchains will need to do a migration or hard fork in order to fix that problem. The hashing they use, perhaps say you're saying for like the consensus side of things, well, I mean, there's a bigger problem with the power consumption that Bitcoin is using. But if you start to move into like proof of stake, then it goes back to the digital signature problem of ECDSA. So there are going to be upgrades that's going to happen over the next 3-4 years. If you follow Vitalik's blog, I think the latest one he called the splurge, which mentions a bit about the whole quantum side of it. So you need to start going into things like zero knowledge proofs, stacks, and other things as well. Another very, very interesting area, we do have our own solutions on it. I'm not trying to push it out here, but another very interesting area in cryptography that you can work on.
Okay, thank you.
Yeah. So I think we are almost out of time. I have my contact, I mean, you can email to info or something like that. If you want the slides, I'll be happy to email it to you. Reach out and just say hello, and then I'll email you the slides as well. And thank you very much for attending. It's been very exciting.